sometimes proving the obvious is harder than proving the less obvious. P implies Q, if I'm not wrong. Oh, I'm sorry, this is P and Q. There you go. P and Q. Yep, yeah. Yeah, all right. So how do we prove this theorem? Well, this is a conditional theorem, so therefore you start assuming with this guy, not P. All right, so this is argument in line 1. All right, well, there's nothing I can deduct from this, right? So that kind of is a good sign that, well, this is not a conditional sentence. So therefore, I cannot make any assumption. So direct proof is not going to help. So therefore, do the indirect proof, which means deny your conclusion, all right? Proof by contradiction. It's widely used proof approach. So how do I prove? Well, as I said, you deny the conclusion. So not P and Q, all right? So this is an assumption for indirect derivation. By the way, some philosophers and mathematicians actually reject the idea of proof by contradiction because they say, well, if you can't prove something directly, that means you can't prove it. Well, I mean, not in this course. So assumption for indirect derivation, okay? So that's the assumption. So what I want to do, so I deny the conclusion. Well, I need to get some contradiction. Okay, and what do we mean by contradiction? Contradiction is the following: if some argument is true and its negation is true as well, this is impossible because remember our atomic sentences and therefore our complicated sentences cannot be both true or false. They're either true or false. So therefore, I can never have a statement is true and its negation is true at the same time. So I assume not P and Q. The third line, I'm going to simplify this, so it's P and Q. Okay, so this is just simplification of the argument in line 2. Well, what is in line 4? I'm sorry, this is not simplification, this is a double negation. Double negation. So this is simplification, double negation of argument in line 1, simplification of argument in line 2, and well, obviously I can also write Q, simplification in line 2. I don't know if I'm going to use it, but hey, okay, I found the contradiction, right? Because remember, I started an assumption. So this is, by the way, assumption for conditional derivation. So I already started with not P, and at some point I showed that P is true. So P is true, its negation is true. Well, this is a contradiction. You don't have to, but let's write not P here again. So this is just repetition of the argument in line 1. So P is true, not P is true, can't be the case. So I got a contradiction. What does that mean? That means, look, if this assumption is true, all right, I reach some sort of a crazy situation where a statement and its negation are true at the same time. So you know what? Here the mistake, I mean, not P cannot be the cause of this contradiction because not P is coming directly from repeating this argument. Q cannot be the cause of this contradiction. Why is that so? Well, because I derived Q, all right, by the simplification rule. I mean, it's a rule. If this guy is true, Q must be true by the simplification rule. P cannot be the cause of this contradiction because, again, I derived it from this argument. If P and Q is true, P must be true, thanks to the simplification argument. So I did no mistakes. Well, can this be because of P and Q is a true argument? Well, it can't be because it's simply the double negation of the first, the second argument. So if this is true, this must be true again. So therefore, here in this box, if I reach a contradiction, this guy is the bad guy, all right? So that means this guy shouldn't be true because being this guy, I mean, the truth of this argument is making my entire argumentation collapse. So this must be false, okay? So I close the box and come back to my line 7 and say, hey, look, if this is false, that means that was my conclusion. I deny it. So denying leads me a contradiction. So I shouldn't deny it. That means not P and Q is a true argument. So you know what? If P is true, well, then this is true as well. So I completely close everything. And then in line 8, I say, you know what? Not P implies not P and Q. So I prove this theorem. All right? Any question? All right. Let's prove the following. Assuming that I didn't do that. P and not Q implies not P implies Q. Well, not, there you go, P implies Q, so be careful, right? Yeah, okay. So let's prove this. So once again, because this is a conditional statement, I'm gonna start, oh, by the way, I mean, it's always good to write the explanation here, how we prove these arguments. So this not P and Q, this is indirect derivation thanks to arguments between 2 to 6. And this is conditional derivation thanks to argument between 1 to 7. Okay? So here, the first assumption is P and not Q. So this is assumption for conditional derivation. Very well. What else? Thanks to this assumption, I know that P must be true. This is simplification of the argument in line 1. And not Q is also true. This is simplification of the argument in line 1. But that's it. So now I need to show this, but this is not a conditional statement. I mean, it is conditional, but this conditional guy is within the parentheses and there's a negation in front of it. So I cannot really assume P. All right, that's very, very important, guys. So when I have a statement like not P implies Q, so I can start assuming not P and then show Q. But here, this negation is outside of the parentheses. All right. So therefore, I cannot assume P, for example, because this not, how is it going to be distributed? I don't know. Okay. There are rules. Obviously, we can prove theorems how this negation can be distributed. But I'm not going to talk about all these details because, well, I mean, this is not a logic course. So therefore, if the statement is something like this, I cannot assume P and then show that Q is true, all right? So be very careful about this. But what I can do is deny my conclusion. So what does that mean? That means in line 4, I'm going to deny my conclusion, which is P implies Q. So assumption for indirect derivation, okay? What else? Well, double negation. This means P implies Q is double negation of the argument in line 4. So P implies Q must be true. What else? Well, you can either use modus ponens or modus tollens. Doesn't matter. You're going to reach contradiction anyway. I'm going to use modus ponens. So in line 6, because P is true and P implies Q is true, so Q must be true. Modus ponens between the arguments 2 and 5. All right, and then line 7, I'm going to repeat argument in line 3. So just repeat. So there you go. I have Q true, not Q true. This can't be the case. So these are not the cause of the contradiction because not Q is just coming from here. Q is derived from this and this. So if these guys are true, Q must be true. P implies Q coming from the double negation of this guy. So if this guy is true, this guy must be true. So therefore, the mistake or the problem should be occurring because of this assumption. Hence, line 8, I'm going to close this. Line 8, I'm going to say, you know what? I shouldn't be denying my assumption P implies Q. So this is indirect derivation between the arguments 4 to 7. Right? So what does that mean? That means I can actually finish my proof because line 9, if P and not Q true, well, I just proved that not P implies Q is also true. If this is false, this argument is true anyway. So that means this argument is true always. And hence, this is the proof of this theorem. One important thing is if we need to continue beyond this line 9, I cannot use any of these lines. All right? Why is that so? Well, whenever I have assumption for conditional derivation, assumption for indirect derivation. So once I have an assumption, the following arguments, until I close this box, are not usable later. All right? That's important. So once I close those boxes, I cannot use them because they are assumptions. They are not true necessarily. Okay? Any question? So, well then, I have one more exercise, which is from section 8, which has probably the most complicated, theorems and proofs because it's biconditional. Which example I was planning to solve? Yep, that one. All right, so here is the theorem that I wanted to prove. This is the third problem in the section 8. So P and Q, if and only if, meaning equivalent to, not P or not Q. Okay? So how do we prove if and only if statements? Simple. Because the if and only statements or the equivalence statements are, both ways. So this implies this is true. This implies this is also true because they're equivalent. So I basically divide the proof into two parts. Part 1, I show the one direction, and part 2, I show the opposite direction. All right. So I'm going to start with line 1. I'm going to prove this part, meaning P and Q implies not P or not Q. So that means I'm going to start with assuming P and Q. And this is assumption for conditional derivation. By the way, again, I keep doing this. So this final line, once I close this, remember I started with assumption with conditional derivation. So this is conditional derivation between the arguments 1 to 8. All right, always write down the explanation just to understand why the argument is true. Is it because I'm using a rule, or is it because I maybe made a mistake and so my explanation is wrong? All right. So therefore, this is how other people can read your proof and see whether you're making a mistake or not in your argumentation. So you have to be specific about what rule you're using. You shouldn't be making the other guys second guessing your way of proving an argument. Okay, so I assume P and Q, and I want to show this. So this is going to go with indirect derivation for sure, right? But let's start with simplification, right? If P and Q is true, P must be true. So the simplification of the argument in line 1, and well, similarly, Q must be true. Simplification in line 1. What else? Well, that's it. I can't really make any other assumption. So what I'm going to do, I'm going to deny my conclusion. So it's not P or not Q. All right, so assumption for indirect derivation. Very good. So this is double negation. So therefore, not P or not Q must be true. So this is double negation of the argument in line 4. Okay, what do I have? All right, so this is a rule which I haven't used up until this point, which is called modus tollendo ponens. Oh, The Latin names is just killing me. I know. Well, again, you don't have to memorize them, but what does it say? Look, P is a true statement, so not P must be false, right? But this is true. You know, this is a false argument or something, so this is a true argument. So therefore, this something must be a true argument. Okay? So this is line 6. Not well, if P is true, not P is false, therefore not Q must be true. So this is modus tollendo ponens between the arguments 2 and 5. You may say, why don't I use Q and this? You can, then this is not P. So you're going to reach the contradiction anyway. So there's no just one way of proving an argument. There are multiple ways of proving it. So you could go that way, no problem. 7. I repeat line 3. All right, Q. Repeat line 3. I have a contradiction. Q and not Q, both true at the same time. Impossible. This can't be because of this, or this, so it must be because of this. So denying the conclusion, which was this, is wrong, so you shouldn't be denying it. 8, I close this. Where am I? Not P or not Q, therefore, is true thanks to argument indirect derivation between 4 to 7. What does that mean? That means, remember, so this is the first box I started, and then this is the inner box, and then now I can close my first box. So this is line 9. I'm going to say, hey, look, if P and Q is true, well, then this guy is true. So P and Q. If P and Q is true, well, then I just showed that not P or not Q is also true. If this is false, who cares about this? This is true argument anyway. So this is thanks to conditional derivation, right? I started with assuming for conditional derivation. So conditional derivation between arguments between line 1 to 8. So that is the first part I wanted to prove. Now I'm going to prove the second part. So I'm going to start line 10. So good question. Can I now, for example, use any one of those lines? Can I contradict with any one of those lines? No and no. You cannot use any of these arguments except the argument in line 9. Why is that so? Because line 1, so everything basically starts with an assumption. It's like, what if the God exists? And then blah, 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 blah. Well, then the conclusion, whether the God exists or not, you know what? This is true. Okay? So once I'm over with this, in the next argument or the deduction, I cannot come back here and say, hey, P. Well, yeah, but P is true if God exists. What if it doesn't? All right, so you see what I mean? So for that reason, because everything starts with an assumption, okay, you cannot use any of those arguments that follows an assumption once the box is closed. So in line 10, you basically actually erase everything, all right? Think it that way. So in line 10, maybe I should do it. So instead of erasing, I should just jump to the second part of my board and continue line 10 and so on here. So in line 10, I want to prove this guy implies P and Q. So that means I'm going to assume not P or not Q. So this is assumption for conditional derivation. From this, I cannot deduct anything. So I have to make some sort of assumption. All right, what I want to show, I want to prove that P and Q. So what I can prove, one way you can say, hey, why don't I take the, deny P and Q? Yeah, sure, you can do that. Or separately, you may want to prove P first, and then Q second, And then because it's and, P and Q must be true. All right? So how do I prove? So therefore that means you can prove individual sentences. So how do I do that? Well, I want to prove P, but I'm going to do it by denying this conclusion. All right, so line 11, I open a new box. I'm going to assume not P. Again, my purpose is to prove P, but let's deny it. Okay, not P. Okay, so this is assumption for indirect derivation. What am I going to get out of this? Well, look, if not P is true, not P or not Q, whatever Q is, not Q may be true, may be false, I don't know, but anyway, this or statement must be true, right? P or Q is always true if one, even P or Q is true. So, what was the rule for this? Was it disjunction? I forgot. I'm sorry, I'm terrible with names. Of the line argument 11. Oh, I'm sorry, this is addition, yeah. This is addition, yeah. So I add another statement, whether it's true or false, so this must be true. Well, you know what? In line 13, just repeat this guy, not P or not Q. So this and this, I mean, the negation of this statement cannot be, so I'll just repeat 10. They can't be both true, so therefore the problem must be arising because of this assumption. So not P should be false, meaning P must be true. So I'm going to call this 11 and go ahead. Oh yeah, okay. First off, this is not 11, I'm sorry. This is 14. Okay, so your question is, why? Well, okay, good question. I mean, I want to prove, remember this statement, P and Q. So how can I prove P? So I want to prove P first. So I want to prove P directly or indirectly. So I prefer to prove it indirectly. So therefore, in order to be able to prove P, I assume the negation of it. So I deny my conclusion. So I assume not P, and then the arguments follow, and I reach a contradiction, which means not P has to be false, therefore P must be true. Sure, you can do that. This is another way of proving this argument, but trust me, this is easier, I think. Or, I mean, it's maybe better. You'll see. I mean, just give me a few more lines. You'll see where I'm heading. So P is true. Okay, so this is thanks to indirect derivation between the arguments 11 to 13. All right, good. I have P being true. Now I want to prove that Q is also true. How am I going to do that? Exactly the same way that I proved P, meaning I'm going to deny my conclusion. So line 15, I'm going to assume not Q. So suppose Q is not true. All right? So meaning not Q is true. This is assumption for indirect derivation. So if not Q is true, I can just add anything I like to not Q. So I'm adding not P. That's going to be still true. This is addition rule. Addition to line 15. So in line 17, I'm going to repeat, okay, so I'm going to repeat what? I can't repeat anything in this box. So let me just cancel everything here because I already closed this box. So that means I can't use all these arguments. But I can repeat 10 because the box, remember, the second part of the proof is not closed yet. So I'm going to repeat this. So this is repetition of line 10. So that means, guys, I got exactly a kind of a similar contradiction, meaning not Q should be false, implying in line 18, Q must be true. Okay, what else? Oops, okay, I'm not closing any box yet. Line 19, I'm going to say, look, P is true under the assumption that not P or not Q is true. I just proved that P must be true, Q must be true. So if both are true, that means P and Q is also true, right? By the way, this is thanks to indirect derivation between the arguments 15 to 17. And so this is a conjunction. I just add them up. The arguments 14 and 18. So P and Q is true. What did I get? Look, I assumed this, and I assumed this true, and showed that this must be true. So therefore, now I am closing this entire box. And in line 20, I say, look, if this argument not P or not Q is true, well then P and Q must be true as well. If this argument is false, no, who cares? This argument is true anyway. So this is conditional derivation between the arguments 10 to 19. Okay, so am I done? Well, kind of. I proved the first part, meaning P and Q implies not P or Q. I also proved the second part, not P or not Q implies P and Q. So therefore, in line 21, I can say, look, P and Q, if and only if, equivalent to this guy, not P or not Q. And the rule that I use for this is bijection. Bijection, I guess, right? Biconditional, I'm sorry. Biconditional of the arguments 9 and 20. And so that's it. This is the conclusion. And that's the proof of this theorem. Yes, it's relatively longer than the others, but this is how we prove an if and only statement. Obviously, it's longer simply because it has two arrows to prove to.